The purpose of this lecture is to do a few more examples of proofs by induction and also maybe introduce a few typical mistakes where if you're not careful it can lead to proving something that's very incorrect. So let's start with a problem, and this is actually a good problem for you to pause the video after I write it out and try yourself. So in this one, I want you to first see if you can find a formula. Find a formula for the sum of the first. So we already did the sum of the first n numbers. Let's do the sum of the first n odd numbers. So some formula in terms of n. Then see if you can prove your own formula. So then prove your formula. So I'll give you a chance to think about this and pause the video if you want to, then we'll come back. Okay, so let's actually start by trying to find the formula. And the way I like to usually do this is just try out a few small cases. So sum of the first one odd numbers, that's 1. Sum of the first 2 is 4. The sum of the first 3 is 9. I think I might see a pattern here, but let me try one more. The sum of these is, let's see, sum of these is 9 plus 7 is 16. And that confirms the pattern that I noticed in the first tree. It looks like these are the square numbers. And which square number do we get? So it looks like the sum of the first 4 is 4 squared. So that's going to be our guess. So here's our guess. The sum of the first... Let's see if we can write the sum of the first n odd numbers. And so in order to write the sum, I can use a dot, 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 because I don't know what n is. And what is the nth odd number? This helps to look at an example. So it's either 2n plus 1 or 2n minus 1. So this was the case for n equals 4. The nth odd number was 7. That's 2 times 4 minus 1. 2 times 3 minus 1 is 5. 2 times 2 minus 1 is 3. So I think we want 2n minus 1. That's my nth odd number. And our guess is that this sum equals n squared. Let's prove it. So sum of the first, what do we start with? We start with our base case, always. The sum of the first 1 odd numbers on the left is that equal to 1 squared? Yes. Checks out. Next, we do the inductive step. And recall, what do we do in the inductive step? We suppose the formula works for some k. So suppose for some k in the natural numbers, the following is true. 1 plus 3 plus 5 plus, I'm just going to kind of copy out my formula again, but with that k plugged in, equals k squared. Then what do? We try to show that the formula works for k plus 1, but we don't assume that. We're assuming this is true. But I'm going to start maybe with what the left side of my formula would look like for k plus 1. And so I'm going to actually write out the whole formula, including this, because I think that'll help me. And then I'm going to write the next odd number, the k plus 1 odd number. You could just plug in k plus 1 there, or you can realize, oh, it's going to be 2k plus 1. Either way, you should get 2k plus 1 for the k plus 1 odd number. And what is this equal to? Well, I'm going to try to use this fact here, especially since I see the left side just sitting there. That's equal to k squared plus the 2k plus 1. But I immediately recognize this as factorable, right? It's the square of k plus 1 squared, which, incidentally, that's exactly what we were trying to prove, right? We're trying to prove the formula worked for k plus 1, so it should have given me k plus 1 squared. So we're done. That was a quick one, actually. Okay, let's do another example where we maybe need to use strong induction. And this is going to be, call this the chocolate bar problem. So starting with a chocolate bar. This is a rectangle, let's say, so an n by m chocolate bar. And the question is, what is the minimum number of breaks? Number of breaks needed to break the bar into individual pieces. I have a demonstration, actually, if you're a bit confused about what I mean. I've got a chocolate bar here. So here's a 3x4 chocolate bar, and we want to know what the minimum number of breaks. So a break is you have to break completely across. So I can break down this one. I can't just break off this corner piece. That would be hard to do. So you have to break completely across the line. And we want to know what's the minimum number to break it into individual pieces. So I'm going to try. I'm going to keep track of the breaks. I'm going to try to do the best I can. So maybe I'll start by breaking here. So that's 1. Maybe I'll break off this row of 3. That's 2. 3, 4, 5, 6, 7. Let's do this. 8, 9, 10, and 11. Looks like I needed 11 breaks. And you can try this problem yourself, especially if you like chocolate. You should try this next time you have a chocolate bar. But it will turn out that starting from a 3x4 bar, you always get 11 breaks, which seems to be, so just over on the side, it seems like that 11 is 3 times 4, which is 12 pieces total, minus 1. So that seems to be the formula for a number of breaks. So let's make a guess here. So our guess is, you can try this with different size bars too. It'll always seem to work out this way, no matter how you do it even. So a theorem is, or a guess for a theorem, it's a conjecture at this point, but a chocolate bar of, say, how do we say the size? Maybe I'll say the total number of pieces, so total area. If area n requires n minus 1 breaks, 1 less break than a number of pieces. And we'll try to use induction. So here's going to be our proof. We start with the base case. A chocolate bar of 1 piece. Here's my chocolate bar of 1 piece. How many breaks does that require to break it into individual pieces? None. There it is. Right? And it requires 0 breaks. And what should we point out? And 0 is 1 minus 1. Right? The formula works. Okay, and then the inductive step. And I already hinted that we might need strong induction for this, but I really want you to understand why we're going to need strong induction. And it's because, what does the problem, for example, for a 3x4 chocolate bar with size 12, what does that have to do with a chocolate bar of size 11? The answer is actually absolutely nothing. It's actually impossible to break a 3x4 chocolate bar into a chocolate bar containing 11 pieces all at once. Because again, you can't break off the corner piece, for example, just on its own. But we do want to reduce the problem to smaller cases, just not necessarily the very previous case. We might maybe want to reduce the problem to 2 smaller cases, because that's what a break does, right? It might break a, let's say we have the 3x4 chocolate bar. So we might break it. I think my first break was maybe here. And so we broke it into a chocolate bar of size. We had one of size 9 over here and then one of size 3. And these numbers have to add up to the total area. So we're going to assume in our inductive step that, suppose for some k in the integers, or natural numbers, so for some, for k in the natural numbers, any chocolate bar of size anything up to k, so 1, 2, 3 up to k, so strong induction, requires one fewer break than the number of pieces, right? That's our formula. So I don't want to call this something. Let's just say that. So it requires one fewer break. Formula is easy enough to put in words. One fewer break than a number of pieces, whatever that size is. We're assuming it for all natural numbers up to k. This is a strong induction. We're using the full power of induction here. Okay. And then we'll consider, so that's our inductive hypothesis. We're going to consider a bar with k plus 1 pieces. And let's break it any way we want. So break it anyway. Let's break it however we'd like. However we'd like. It doesn't matter. Into, the key is you break it into two smaller bars. Both of them are smaller. A and B. Let's call the bars A and B. With little a and little b pieces, respectively. And what do we know about these numbers a and b? They have to add up to k, right? Or they have to add up to k plus 1. So with a plus b, they have to add up to the total area. Equals k plus 1. Then the total number of breaks, total number of breaks for the bar of size k plus 1 is, let's try to figure that out. So I've got my chocolate bar A. We're assuming, because that's some number between 1 and k, it's definitely less than k plus 1, we're assuming that takes a minus 1 breaks. That's our assumption in strong induction. Okay, so this is for bar A, number of breaks for bar A. And bar B, similarly, will take b minus 1 breaks, again, by our inductive hypothesis. But we also have the one break we just did, right? So this was the break we just did. We just made. Okay, and what does this add up to? Well, it adds up to a plus b plus, let's see, 1 minus 2 is minus 1. But this is k plus 1 minus 1, which is k, which is what we wanted to prove. We wanted to prove that a bar with k plus 1 pieces will require one fewer breaks, which would be k. Okay, so that is the end of the chocolate bar proof. So maybe now I'd like to address a few common mistakes. So the first mistake I'll point out is actually a very common one. The second one is rather subtle, but it's sort of a famous problem, so I definitely want to mention it. So here's a common mistake, and I'm gonna give you a proof of the following theorem. You can see if you can find a mistake if you like. So I'm gonna prove that the polynomial n squared plus 5n plus 1 is even for any natural number n. Okay, here's the proof. So we're going to use induction. So How does induction work? Well, we're going to assume that it's even for some k. So we're going to assume that k squared plus 5k plus 1 is even for just k and the natural numbers. And then I'm going to prove that, what do I want to do? I want to prove that it's even for the next k. So I'll plug in k plus 1 instead. And we expand this out. We get k squared plus 2k plus 1 plus 5k plus 5 plus 1. Let's collect the like terms. 7k plus 7. And I'm not sure whether or not this is even. I want to use my inductive hypothesis somehow. So here's how I'm going to use it. This is kind of a typical idea. It's a nice idea, though. I'm going to make this polynomial up here. So I'm going to write 5k, and I'll put a 2k over here. And I need to do plus 1, and then what is left over is a 2k and a 6 in order to make that 7. So that's the same thing as the previous line. I just rewrote it in a clever way because now I can say this is, this is 2 times k plus 3, and this is just the same polynomial. And that proves it because this is even. This is even, clearly, because k is a natural number, and it's 2 times something, some natural number. And the sum of even and even is even. So that proves it. Okay, did you notice the mistake? So it turns out this argument is airtight here. There's no, unless I accidentally made a mistake here, but I believe this should be an airtight argument here. We did, in fact, prove that if this is even for some k, then the next one is even. The problem is there was no base case, right? And you might say, so wait, there's no base case. But you might say, well, wait a second, a base case just always seems easy, right? Like, why do we really need to do the base case? It's just always like the simplest case to do. Well, this example shows why. Because when you actually take a look at this polynomial and try to figure out the values of n for which it's even, this actually turns out to never be even. So that's so we proved something completely false. This polynomial is never even. So actually, n squared plus 5n plus 1 is never even. The base case is very important. So the base case is important. It's essential even in order to write a proof, a correct proof. And so this was like when we had the, let me grab my dominoes over here. So it's like when we had the domino example, right? So induction you can think of as some dominoes, and they're all set up to follow over. And they might be set up perfectly, but the base case, think of the base case as actually pushing the first domino over. If you never push the first one over, even if they're set up perfectly, they're never going to fall down. So the base case is actually proving the statement is true for some value. We're actually pushing it over, and then that sets off the chain reaction, which is induction. Okay, let's do one more example, and this, as promised, this is a famous example. So this one is another theorem. It's another fake theorem. Yeah, I should emphasize this is a fake theorem. And this one I probably won't have to tell you it's a fake theorem after I say what the theorem is, because it sounds completely ridiculous when I'm about to say it. So the theorem is all horses are the same color. But I'm actually gonna prove it. All horses are the same color. This is a bit of a famous problem. Sorry about that. It's possible you might have seen this before. In any case, so you can try to figure out the mistake as I prove it. So here's my proof. I am not going to try to be sneaky with the base case, so I will do a proper base case this time. The base case is, so for n equals 1, and what's the theorem I really want to prove? It's, so I'll try to prove any group of n horses is all the same color. Okay. And if we're talking about all horses, it's just a statement for a very large n. So base case, any group of one horse. Well, I'm sure you would agree that any group of one horse is all the same color. All right. There's just one horse, so it's just whatever color the horse is. The horses. And I know there can be horses that are multicolored, so for the purpose of this problem, just assume every horse has one well-defined color. So whatever color that horse is. And then the inductive step, what do we do with the inductive step? We assume that a statement is true for k. So assume that any group, I'm not even going to need to use strong induction here. I'm just going to use usual weak induction, I guess that's what it's sometimes called. So any group of k horses has the same color. Great. Okay. And I want to consider a group of k plus 1 horses. So consider a group of k plus 1. I should just be clear. So I'm not saying every single group of k horses is the same color as every other group. I'm just saying within each group, any group of k horses is all the same color. Let's say. And consider a group of k plus 1 horses. So I'm going to draw a picture. So that might look like this. So I'll have some horses. Maybe I'll do the case for k equals 5 just to be able to draw a picture. So I have 6, so I'm considering one more. And here's the argument. I'm going to try to reduce this to the case of k horses, which we're assuming. And I'm going to choose k of the k plus 1 horses, right? What do we know about these? These all have the same color. By our inductive hypothesis. These have the same color. And I'm actually going to call that color something. Let's call it C. Okay? So each of these has color C. C, 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 C. I don't know what the color of this other one is. However, I'm going to do the same thing. But now I'm going to be sure to include that other one. So I will do this group of 5. It's not important which group I do, though. I just want to make sure I include that one. And what is the conclusion? Well, we have assumed that any group of k horses is all the same color. And this group has horses with color C, so that means this one must also be color C. So all the same color, right? That group itself is all the same color, which must be that same C. Okay. Because otherwise this group would violate the inductive hypothesis. So that's it. We just proved that. So any group of k plus 1 is all the same color. So you might have found that a really convincing argument. And it turns out this picture and the logic that I use here is totally correct when it comes to this picture. And the base case is also correct. Feel free to pause the video if you want some more time to try to find find a mistake. It's a bit subtle, but I'm about to say what it is. So, again, it's a very subtle mistake. This picture, although accurate for large numbers of horses, is actually a bit deceiving in one particular case. And that is the case k equals 1. So for going to k equals 1 to the next number, which is k equals 2, here's what this picture would look like. So I'm assuming that every group of 1 horse has the same color, but there's a group of 1 horse and there's a group of 1 horse. Right? Unlike this picture, these groups do not overlap at all. So I cannot sort of use the inference to translate something about this group into a statement about that group. And so this actually fails. The argument fails. So the inductive step fails. It fails for exactly k equals 1. And it works for every other value of k, which is why this is pretty subtle. It's pretty difficult to detect the mistake here. And so in the dominoes example, that might look like I've got my dominoes set up. These are a bit hard to set up. Hands are a bit shaky too. But let's say I've got one over here. So this is the first domino, second domino, third domino, and maybe everything after that is set up beautifully. But the first one, I am going to knock it over, but it does not trigger the second one. Right? And so that's the problem here. Everything else is set up perfectly, but this first one, even when I tip it over, it does not trigger the second one. And so that's another thing to be careful about in induction. You really have to make sure your group works for any arbitrary k. And this argument, it turns out, the picture was a bit deceiving. It did not work specifically for going from k equals 1 to 2. Okay, so hopefully you enjoyed this video. I'll see you in the next one.